Hello anatomy students. Today I wanted to go through reactions 5, 6, and 7 in the reaction type lab that we did in class over the last couple of days. So we have already filled out part 1 in class together, but I did want to just take a look at number 3, the single replacement reaction that I have here. Because I just wanted to make sure that you understood something. In a single replacement reaction, you have an element being added to a compound. And if the element is higher, like if the metal that stands alone is higher than the metal that's a part of the compound on the activity series, then you're going to get a reaction. But sometimes the reactants are not written in an A plus BC form. Sometimes the element is written after the compound, like this, where you have AB plus C yields CB plus A. So even in this case, you still have an element being added to a compound, but it's still single replacement. You still have the element removing the metal from the compound, again, if it is higher on the activity series, and then you get products. So I just wanted to make sure that you understood that in a single replacement reaction, regardless of how the letters shake out, your reactants are always an element and a compound, and your metals are going to switch places. Okay, so let me pause it for a moment. I'm going to scroll down to reaction 5. All right, in reaction 5, we are combining hydrochloric acid with magnesium metal, or Mg. Don't worry about the concentration. That does not matter at all. So what we have here is HCl plus Mg. And we need to see if we can predict the products. The first thing that we have to do is assign letters to each element. So we'll call hydrogen A and chlorine B, and we'll call magnesium C. So we have AB plus C. If we scroll back up to our first page, we can see it's not synthesis, because synthesis is A plus B. It's not decomposition. But let's look at single replacement. We have hydrochloric acid, which is a compound, and we're adding magnesium to it. So we have an element and a compound, so that fits right here. And if we take a look, we wrote it HCl, AB plus C. So this is the general form of a single replacement reaction that we want to follow. This means that our products are CB plus A. So let's go back to number 5. Where our general form then is CB plus A. Now all we're doing is matching. We said that C is magnesium. We said that B is chlorine. And we said that A is hydrogen. Now you have to first check your activity series to make sure that this works. And if you look, you'll see that magnesium is indeed above hydrogen on the activity series. So yes, magnesium can kick out and replace hydrogen from chlorine. Okay, the next thing that we have to do though is we need to make sure that our compounds are neutral. We have to switch the charges. Well, magnesium has a charge of +2 and chlorine has a charge of -1. So in order to switch the charges, we need to bring the 2 down here and the 1 over here. And when we do that, we get a formula, we got to erase our charges, of MgCl2. And I want to make that green. Sorry, folks. There we go. So this is the formula for magnesium chloride. And this should make sense. With 1 magnesium, we have a charge of +2. And if we have 2 chlorides, we have 2 ions that are a -1 charge. And if we add them all together, we get 0. And that's exactly what we want. But now let's look at hydrogen. Hydrogen is what we call a diatomic element. it cannot stand alone. You need to pair it up with another hydrogen. So the formula for hydrogen is actually H with a subscript of 2. Now, diatomic elements are hydrogen, iodine, bromine, oxygen, chlorine, and fluorine. And here's hydrogen. So if you've got an element standing by itself and it's a part of high Broncliffe, you've got to put a little 2 next to it. Okay, so we've already figured out that this is single replacement, by the way. All right, now let's balance this. When we make our grocery list, we have H, Cl, and Mg on both sides. And on the right, we have 1 of each. And on the left, we have 2 hydrogens, 2 chlorines, and 1 magnesium. So how are we going to get 2 hydrogens and 2 chlorines on my reactant side? Well, just put a coefficient of 2 there. And then that is going to change our hydrogens and our chlorines. And guess what? We are now balanced. So we have a single replacement reaction, and we've written out the full balanced equation. Good job, guys. Let's move on to reaction 6. With reaction 6, we are doing a reaction with the hydrogen gas that we produced in the reaction, numbered reaction 5. So what we're doing here is we're taking the vapor and we're lighting it on fire, which means that we are adding oxygen to it. And we are going to produce water droplets. So we get H2O or water. Now guys, this is a synthesis reaction. And this was a hard one to predict the product for. So like without your notes or anything, I wouldn't ask you to know how to do this one in particular. But since I'm telling you that the product is water, we can now go ahead and balance our equation. So on each side, we have hydrogen and oxygen. And now we just need to get 2 oxygens on my product side here. So I'm going to put a coefficient of 2 in front of my hydrogen. That changes hydrogen to 4. It changes oxygen to 2. And now to make my hydrogens 4 on the reactant side, I put a 2 in front of hydrogen, and that gives me 4. And now we are balanced. So reaction 6 was a synthesis reaction where we made water out of hydrogen gas and oxygen, which was provided by the flame of the stick. All right. Reaction 7 is also one that's a little bit difficult. And the reason why is because you want to say it's combustion, because you had to light the Bunsen burner and you're adding heat, but actually it's not. We're not actually directly adding oxygen to the dextrose. This is actually going to be a decomposition reaction. Our only reaction, the only thing that we put into the test tube, the only thing was dextrose. And I give you the formula here. We have C6H12O6. We added it to the test tube and we heated it up. But this is just decomposition, guys. And what we got was melted sugar, essentially. And if you had heated it up enough, you would have seen like the charred carbon that would have formed. So basically what we got was elemental carbon and we got water. Again, I don't expect you to know this off the top of your head, so that's why I wanted to make sure to do reaction 7 with you. But what we can do is definitely balance this equation now. So on my reactant side, I have 6 C's, I have 12 H's, and I have 6 O's. And on the product side, I have 1 C, I have 2 H's, and I have 1 oxygen. Well, I feel like the carbons are probably the easiest to balance here because this carbon is standing alone. It's elemental. And guess what? I didn't have to put a 2 here because look, if we look at high Broncliffe, there's no carbon here. This C belongs to chlorine, so I don't have to put a little 2 here. But if I put a 6 in front of my carbon, that means that my carbons are now balanced. And now I want to look at my hydrogens. I need 12 hydrogens on the right. So if I put a 6 here, 6 times 2 is 12. So now my hydrogens are good, but look it. The 6 also distributes to the oxygen, so that means I've got 6 oxygens too. And just by putting in these 2 6's, I now have a balanced equation. All right, chemistry students, that's how you do those last 3 reactions. Make sure that you copy these down on your lab sheet in preparation for our lab quiz that we're going to have on Friday. Take care, and I'll see you soon.